Today, my presentation will cover the cost overruns in the mining industry, the causes, the cases that illustrate them, and how better cost estimating can prevent them. Unfortunately, cost overruns remain common in our large mining projects, and they're only getting bigger. They can be traced back to poor scope definition, inadequate data collection, and engineering. Also, optimistic estimates and not understanding the risk and the contingency of what we're getting into. This presentation will discuss cost overruns in the mining industry using case studies to illustrate recurring patterns and offer practical solutions. A little bit of background information on who I represent. Costmine Intelligence has been around for about 40 years doing cost estimates, and we're based out of Spokane, Washington. We help mining companies, investors, mining consultants, and government institutions make better, faster decisions on costs. Our offerings cover 4 key areas: mining costs, mineral processing costs, reclamation costs, and project data. The first is Mining Intelligence, our database of company and property level information. As most of us know, publicly traded mining companies need to be transparent. That means publishing technical studies, issuing news releases, and reporting drill results. Our Mining Intelligence database is updated daily, giving you access to detailed information by company and by property. It's a great tool for benchmarking technical studies and checking whether your evaluations are on track. We offer Mining Cost Service, which includes data on mining supplies, labor, concentrate transportation, utility costs like power, diesel, and natural gas, and mining-specific taxes. We also offer Equipment Cost Service, which provides detailed cost data for mining and milling equipment as well as specific mining equipment costs. Another product we offer is our Sherpa cost estimating software. Instead of working with static cost models, Sherpa allows you to adjust production rates, equipment, labor costs, and similar variables for open pit, underground, processing, and reclamation scenarios. And finally, our most recent product, Woody. It takes our Sherpa algorithms and allows you to take a technical study off the internet and take a look at how the capital and operating costs compare to what we recommended versus what the mining company is publishing. Comparing Woody to companies, I took approximately 12 development studies from various years and escalated the cost to 2025. They go all the way from PEs to feasibility studies, and we had Woody take a look at what the operating costs would be in this case, and on average, we found that our operating costs were about 39% higher than the mining company's technical studies. We did the same thing for capital costs. These are a little bit more on either side of the zero line. The CapEx included the equipment infrastructure, the design and engineering costs, directs and indirects, and then the project contingency. Off-site infrastructure in some cases, such as the cost of rail, line power off-site to the mine, and ports is not included. We don't get into that level of granular detail, and we're not experts in designing those aspects. In many cases, the technical reports don't include enough parameters for us to build accurate models in that area. That said, we are continuing to build out Woody. Future enhancements will include international labor support. Right now, our costs are US-centric, although we do include quite a bit of Canadian labor data. We also plan to add reclamation costs. Another area we are looking at is brownfields projects. That means figuring out how to model a mine restart compared to greenfields development, which is what Woody currently handles best. So what causes cost overruns? The first is a lack of clearly defined scope of work and design criteria. It comes down to understanding what you are getting into and what you hope to achieve. The next cause is insufficient critical data to support the level of study you're doing, whether it's an early-stage scoping study or a full feasibility study. That includes exploration drilling, geotechnical engineering for pit or tunnel dimensions, high wall stability, and hydrological modeling to understand subsurface water conditions. Metallurgical test work is also important. Can you recover the commodity you're targeting at a reasonable percentage? Another factor is pressure from the client to finish quickly, especially if timelines have already been promised to the market. There is also the push to reduce capital costs. For example, cutting back on the size of a ball mill or primary crusher to save money. That often goes hand in hand with aggressive or unrealistic schedules. It is not uncommon to see companies promise to build a mine in just a year and a half. Some capital equipment can have lead times of 9 months or more, which adds a lot of pressure to stay on schedule. Another issue is overestimating the accuracy of the project at an early stage. Sometimes you're working on a PEA, but presenting it as if it's a feasibility study, even though the cost accuracy range doesn't support that. Another issue is not building in a well-thought-out contingency, and one that comes up often is the lack of external, independent review throughout all phases of the project. When you start a scoping study or a PEA, you should also be doing trade-off studies. The last thing you want is to get to the feasibility stage and have a seasoned reviewer look at your work and ask, "Have you thought of this?" If the answer is no, you're left flat-footed. To avoid that, independent review should be part of every stage in the development of a technical study. Another cause of cost overruns is a lack of understanding of the key project risks. Risk assessments often come up in conversation, things like Monte Carlo simulations to estimate the probability of different outcomes during project development. But in some cases, the project owner or the consulting engineer may not have experience delivering a project, especially in a foreign country where they are unfamiliar with ESG expectations or cultural considerations. The same applies to owners managing large, multi-billion-dollar projects. If you have not delivered something at that scale before and you do not fully understand what you are getting into, the chances of cost overruns increase significantly. Another issue is relying on an outdated technical study. For example, taking one from 2010 and simply adjusting the costs using something like the Consumer Price Index. That approach often overlooks technological advances or the value of having a fresh set of eyes review the designs. There's also the overestimation of labor productivity. In some parts of the world, it simply takes more manpower to move the same amount of rock. You need to understand those regional differences. With that in mind, let's take a look at a few case studies. I'm not looking to call out any specific company, so I'll keep this intentionally general. The first one is an underground open-pit polymetallic mine in East Asia. Reasons for the overruns were the remote location. It impacted the procurement and logistic issues of getting equipment to the site, and the cost of construction also. Power infrastructure, timing and cost related to securing long-term power sources. Before the iron hit the ground, they didn't have their power contracts in place, and it made it very difficult to go forward with constructing the project. In the underground portion of this project, the team encountered unexpected and challenging ground conditions. Since the mining method relied on proper tunnel support, they had to redesign the mine, which impacted both the cost reforecast and the overall schedule. This all took place during COVID, which added further disruption to both the timeline and the project costs. There were also issues with the power contract, including political and contractual friction that affected project delivery. The government had a stake in the project, and tax and royalty disputes followed. These were partly due to some of the shortfalls mentioned earlier. There were also unexpected demands from the government, including a requirement for greater use of local labor. This became especially challenging during construction, given the need to train local tradespeople and build up the necessary skill sets. These challenges resulted in a stop-and-go pattern throughout the project. One of the key lessons learned from this East Asian project is that feasibility studies should include a rigorous risk assessment and account for all major cost and schedule drivers. Independent third-party review should continue as work progresses. I've always felt that a planning session between the consultant who completed the feasibility study and the EPCM or construction team taking over is extremely valuable. The consultant has usually lived with the project and understands it in detail. The EPCM team is often new to it and will have questions like, why was it done this way? Or could we approach it differently? It's important to create space for that kind of dialogue. Finalizing critical infrastructure agreements before breaking ground is important for reducing risk and uncertainty. This includes securing line power and confirming water sources for both construction and operation of the mill and the mine. When project scope is immature or geotechnical conditions are uncertain, contingency risk allowances must be robust. These should be independently reviewed at key schedule milestones. The second case study is an open pit mine in South America. The project faced challenges due to its remote location and very high altitude. The tailings storage facility was in a seismically active area. Capital costs also included a new port and ship loading facility. Power and water had to be distributed from the port up to the mine site at elevation. I believe the project included a desalination plant to supply fresh water to the mine, which added technical complexity in both design and execution. COVID also had an impact. Supply chain disruptions led to contract claims, and isolating workers during construction reduced overall efficiency. There were geotechnical issues as well. Limited data led to pit instability, which delayed access to high-grade ore. As most of you know, getting high-grade material into the mill early is key to generating cash flow. There were also additional challenges with tailings management. Slow sand drainage affected the placement of tailings coming out of the mill, which reduced mill throughput and impacted early cash flow. Contractor performance and equipment reliability were also issues. Part of this was related to COVID, with contractor output falling below plan and leading to contract claims. Some of the capital equipment also had reliability problems, largely due to poor commissioning and startup at the site. Lessons learned from this project include understanding the size, scale, and remoteness of your operation. The time and effort spent on engineering and planning should match the overall complexity of the project. Using Monte Carlo analysis and presenting capital costs in a P50, P80, and P90 format can help identify where to focus your time and effort on the major risks in a project. It is also important to develop contracts and insurance agreements that address pandemics, force majeure, and other unforeseen events in a way that shares risk between owners and contractors. The third case study is an open-pit precious metals mine in Nevada. This was an expansion project. The first cost overrun was due to insufficient front-end work. That includes planning, design, engineering, and metallurgical test work. One example was with the earthworks. Infrastructure was required to support the expansion, and the assumption was that the rock would be easy to mine. That is what I refer to as free mining. The idea was that no drilling or blasting would be needed. Just dig it with a loader, haul it by truck, and place it in the waste dump, but that assumption was wrong. The rock turned out to be much harder, and they had to bring in drilling and blasting, which increased costs and slowed down the work. On top of that, the ore body chemistry changed with depth. The team had to quickly adjust the processing plan to achieve acceptable recovery from the deeper material. COVID also created challenges. Lead times were extended, and workforce turnover made it difficult to attract and retain skilled labor. At one point, a significant portion of the trades workforce dropped off within a single month. I'm not sure exactly why, but it had a clear impact on the overall project schedule. There were a number of important lessons learned from the Nevada project. First, prioritize front-end planning. Robust early-stage work is critical to minimizing costly surprises and delays. Even if you are expanding a long-running operation, you still need to identify the risks and have a clear plan to address them. Second, adapt to changing conditions. Your project plans need to be flexible. Make sure you have solid change order and approval processes in place. Third, monitor progress and costs closely. Use strong project controls, reforecast regularly, and compare your forecasts to actuals. External variables like COVID or force majeure events can disrupt the schedule. You need contingency planning. What is your plan B? What is your plan C? A practical checklist for building better cost estimates should start with clearly framing the project scope and identifying key cost drivers. Identify risks early and plan for them. Build a strong baseline and revise it with updated, detailed cost data. Independent review at key milestones is essential. Calibrate your cost models with current data from tools like our mining cost service and equipment cost calculator. Costs are constantly changing. Run sensitivity analyses to test for what-if scenarios such as shifts in labor productivity, fuel prices, exchange rates, and escalation. Set a realistic and robust budget. Review and update it throughout construction. Finally, develop a contracting strategy and a procurement plan for long lead equipment. Establish a clear change control process and reforecast costs monthly against actuals. In conclusion, most mining project cost overruns are both predictable and preventable when proper scope definition, reliable data, and disciplined execution are in place. Common drivers of overruns include overly optimistic estimates, scope creep, productivity shortfalls, foreign exchange impacts, ESG-related factors, and rework caused by design or construction changes. One way to benchmark against reality is with Woody. It offers an asset-level comparison that helps identify red flags. If a proposed project's operating costs are far outside the benchmark range for similar operations, that may be a sign of estimate optimism. First principle validation is also important. Bottom-up cost estimates for mines and mills provide a strong check against top-down or factored estimates, which often lean too optimistic. When it comes to inflation and indexing, you can use CPIs or PIs, but general consumer indexes are not specific enough. Mining-specific indexes that track labor, explosives, and equipment offer a much more accurate way to forecast cost escalation. Finally, at Costmine Intelligence, we can support your projects with independent reviews, benchmarking, and Sherpa-based cost estimates. Thank you for your attention. Please feel free to reach out to us to learn more about how we can support your project cost planning and estimation.